viewers, welcome to my channel Mugambe Brian. So please like my content and subscribe to my YouTube channel and my TikTok account. Today we are going to continue that discussion, and in this scenario it will involve the eating curve basically. Okay, we have Brian that leaves home for work at 7:20 a.m. and he must carry tea in a flask. So one morning he needed to prepare the tea, however, such that he carries it, but remembered that the only water that he had in the house was 5 liters in a saucepan of 0.2 kilograms stored in a deep freezer. So on removing the saucepan from the freezer, he realized that all the water turned into a block of ice. It was 7 a.m. and he was worried about leaving late, but decided to eat the saucepan containing the block of ice with his, so this was supposed to be his, with his hot plate rated at 4.22 kilowatts until all the ice turned into water and the water boiled, ready for the tea. So we have a hint with us. We have the specific heat capacity of the saucepan is 900 joules per kilogram per Kelvin. We have the specific heat capacity of water, which is 4,200 joules per kilogram per Kelvin. We have the specific latent heat of fusion of ice, which is 336,000 joules per kilogram. We have the density of water, which is 1,000 kilograms per cubic meters. We have the boiling point of water being 100 degrees Celsius, and the initial temperature of ice in the saucepan being 0 degrees Celsius. So in this scenario here that we are going to look at, first of all, if you look at the heating curve that you have been looking at previously, so remember this water turned into a block of ice, and therefore we shall supply some heat first of all for the block of ice to change the state from solid to liquid, that is the water, and then after that this water will be heated from 0 degrees Celsius and up to when it hits 100 degrees Celsius, where the water will be able to boil and Brian will be able to get his tea ready. So the task, we have to determine how long it takes for Brian to boil the tea, and then explain whether or not Brian was able to leave home for his work by 7:20. Obviously, when we get the time that it will take Brian to boil this water or the block of ice up to 100 degrees Celsius, so we'll be able to add that time to the time where it started boiling it, which was 7, and then we see whether he will be able to leave home for work early. Okay, so as part of our response, we have to correct the information that was given to us. We have this water here, we need the mass of water definitely, but it has been given to us in liters, and therefore we have to convert those liters to mass, which is in kilograms. However, the density of water was also given to us, so we need to remember all these conversions here. So we know that it is known that 1 liter is equivalent to 1,000 cubic centimeters. That is equivalent to 0.001 cubic meters. And then 5 liters obviously will be the 5 times this value, which is 0.001. And then at the end of it all, this leaves us with 0.005 cubic meters. Then the next step is for us to find the mass of water, that is given by the density of water times the volume. The density was given to us as 1,000 kilograms per cubic meters, and the volume we have gotten it as 0.05 cubic meters. So this leaves us with a mass of water being 5 kilograms. Okay, then we go back to our heating curve. The energy that is required to melt the ice at 0 degrees Celsius, that is the latent heat of fusion, so we shall get it. Remember, it occurs at a constant temperature, that is 0 degrees Celsius. So the mass of the ice, the water that had turned into ice, is 5 kilograms. Remember, we say the mass of a substance remains constant regardless of whether it changes the state or not. It remains constant. then multiplied by the value of the specific latent heat of fusion, which was given to us as 336,000. Then after doing the computations there in our calculators, this leaves us with a quantity of heat which is 1,680,000 joules of heat energy that is required to change the state of this block of ice of 5 kilograms to liquid in this particular case. Then next is the heat energy that is required to raise the temperature of melted ice from 0 degrees Celsius to 100 degrees Celsius. So that is the second section of our heating curve, if you remember. Then that will be given by the mass of the water that we have times the specific heat capacity multiplied by the temperature change, delta theta. Okay, the mass of water is 5 kilograms times the specific heat capacity of water. It is a constant that was given to us, which is 4,200 joules per kilogram per Kelvin multiplied by the temperature difference. So the temperature difference is basically the final temperature in this particular section of the graph, which is 100 degrees Celsius minus the initial, which was 0 degrees Celsius. So doing all the computations there, this leaves us with the quantity of heat, which is 2,100,000 joules of heat energy that is required in order to raise the temperature of the water from 0 degrees Celsius to 1,000 to 100 degrees Celsius. Okay, then we shall also look at the saucepan. Remember, even the saucepan in this particular case is gaining heat as we are supplying that heat. So the temperature is being gained by the heat, rather than saucepan, and at the same time by the saucepan. So we have the heat energy that is required to raise the temperature of a saucepan from 0 degrees Celsius to 100 degrees Celsius. Remember, this saucepan of ours, obviously, it will not suffer change of state in this particular case. So if the ice was at 0 degrees Celsius, then that means even the saucepan itself had acquired the temperature of the ice, which is the 0 degrees Celsius. And therefore, as we heat this water to 100 degrees Celsius, even this saucepan will gain that temperature there. So okay, so but what is that quantity of heat that is required in order to raise the temperature of the saucepan from 0 degrees Celsius to 100 degrees Celsius? So basically it will be given by the mass of the saucepan, the specific heat capacity of the saucepan, multiplied by the temperature change delta theta, which is the final temperature minus the initial temperature. Okay, the mass of the saucepan was given to us as 0.2 kilograms, and its specific heat capacity was 900 joules per kilogram per Kelvin. So doing all the computations there, this leaves us with a value of 18,000 joules of heat energy that is required in order to raise the temperature of 0.2 kilogram mass of a saucepan from 0 to 100 degrees Celsius. Then the final thing that you have to do is to get the total heat energy that is supplied to this system, of course, of the saucepan and then the block of ice. So it will be a summation of all those heat energies. Okay, so you have to sum up all these values here, and at the end of the day, after getting the summation, this will leave us with 3,798,000 joules of heat energy that is required in this particular case. Okay, then the next thing was we're required to find the time that is taken in order for Brian to get his tea ready. I'll remind us that we know that the power supplied to the system is basically energy, which we are denoting as E, then divided by the time t. Okay, we know that power is basically the rate of doing work, which is basically work done over time. So it can be work done is in joules, so it can be energy over what? Over time. And this will imply that our energy, remember what we have gotten is the quantity of heat energy. So heat energy will basically be the power times the time. Remember the electrical heater, which is rated 4.22 kilowatts. It's the one that is heating the water first of all and the saucepan at the same time. So the quantity, the power that is being supplied by the heater is equal to the energy, the quantity of heat energy divided by the time taken. Okay, so this will imply that when you cross multiply, so the T will come this other side and then the P will come down. So the time taken to supply the heat energy will be basically be the quantity, the total heat energy divided by the electrical power supplied by the heater. Okay, in this particular case, so we have the electrical power of the heater is 4.2 kilowatts, but remember power has to be in watts, and therefore you have to convert the 4.22 kilowatts to watts multiplied by 1000, and then the quantity or the total heat energy was this value here. So we bring it and then we substitute it. So we have T standing in for our time taken, and then making the T the subject, this leaves us with 900 seconds. And yeah, we can convert the 900 seconds, to minutes. Okay, this leaves us with the time being equal to 900 seconds. So we know that 1 minute is equivalent to 60 seconds, and therefore when you happen to divide this value by 60 seconds, this leaves us with 15 seconds, and therefore it took Brian 15 minutes, it's 15 minutes. Therefore it took Brian 15 minutes to boil the tea. Okay, so our next part, we're to find whether Brian will be able to leave early for work. Okay, so remember Brian started eating the tea at 7 a.m. and the tea was boiled for 15 minutes, and that implies that we shall add the 7 a.m. plus the 15 minutes, and therefore that makes it 7:15. So Brian will be able, this is not a she, so Brian will be able to leave home for work by 7:20. Reason being, he has been able to eat the water, or he has been able to get his tea ready by 7:15, and therefore he will be able to leave home for work by 7:20 a.m. Thank you so much for watching. Please do wait for other videos explaining this particular concept here. Wish you well.